So I should apologize to those of you who have seen me give talks like this before. It's a long story. I'll set the stage, tell you about a lot of the things we've done over the past, 15 years now, going up through things in the last year. And Christian will go into more detail. So I am going to talk more about Graphons, and he's going to talk more about Graphexes. Okay, so the motivation originally, 15 years ago, was three related problems. What's the correct notion of a limit of graphs, which preserve the essential properties? And then more recently, maybe in the past 5 or 6 years, for sparse graphs of unbounded degree. How do I non-parametrically model large-scale real-world networks? So how do I come up with random graphs that reflect these graphons? And how do I estimate or learn the representations for a graph? And then can we use graph limits to construct algorithms? And I will use the slides, some of the slides that Christina gave this morning with less detail because you should know it all from Christina. Okay. She was generalizing to tensors. I'm just going to do the graph case. Okay. So a graph is a vertex set and an adjacency matrix telling us what is connected to what. And a graphon, in general, it lives on a sigma finite measure space, and it's a symmetric measurable function. So from a graph, we get a graph limit, a graphon. From a graphon, we could generate non-parametric random graph models, which are consistent with that. And also, given a graph, how do we use graphons to estimate that graph and applications? Okay, so I'll first talk about dense graph limits, which was maybe the first 5 to 10 years of our journey. Then I'll talk about notions of convergence for sparse graphs. Then using these graphons for modeling, how do we estimate networks using graphons, and then an application, which is going to be a simpler case of what Christina talked about, of course, in collaboration with Christina and using her slides. Okay, so for those of you, probably a lot of you know, but if you don't, if I took a graph like this graph and, does the pointer work? It does. Okay, and I looked at the adjacency matrix of the graph, and I said, okay, the things where I have a 1, so I have all the sites across the top, all the sites across here. Where I have a 1, I'll color it in. Where I don't, I won't color it in, and I'll take a limit, okay? The random graph, it would just look like a grayscale picture. This is kind of halfway white, halfway black. How about permutations of the vertices? Like this is the same as that, up to a permutation. And so a while ago with Latsi Lovas Sr., we showed, we being always me and Christian, that the limit is unique up to measure preserving bijections, which are the analogs of the permutations. Interestingly, with the other Latsi, who is here at MIT someplace, we did a version of this for Graphexes, which is over 100 pages. It was really difficult to do the analog, but the son can do more than the father, of course. So, okay, so V2. Okay, V2 does more than V1. So our first notion, we called it left convergence, and because what we thought was we thought to study maps from a small graph F into a big graph G, which is equivalent really to looking at so what we did was we defined the homomorphism densities, and we said that if you have a sequence of graphs and the edge density, triangle density, four-cycle density, Peterson graph, all the finite graph densities converge, then we say that this sequence is left convergent or subgraph convergent. There's another notion, which we called right convergence, which was thinking of the big graph having homomorphisms into the small graph. Here you can think of the small graph as representing like a coloring model or a statistical physics model in which, let's say it had 4 vertices, red, green, blue, and yellow, okay? And my little graph would tell me what's allowed to be adjacent to what, for example, okay? So what this turns out to be is the same as looking at what's called the microcanonical ground state energies on that graph, or weighted multi-weight cuts on that graph. So that's why we call it right convergence. The big graph homomorphisms into the small graph, okay? So looking at all the free energies, microcanonical ground state free energies converging is what we call right convergence. So if you have a sequence of graphs and all of these converge for all microcanonical ground state energies with positive weights, with non-negative weights, okay, then we'll call it right convergent. So what is a graph limit? Well, you can think of it from the left convergence point of view as a collection of probability distributions on finite graphs. From the right convergence point of view, you can think of it as a collection of microcanonical ground state energies. Also, you could say that a graphon over a sigma finite measure space is an integrable function. So think of this as the generalization of the adjacency matrix. It's symmetric as an adjacency matrix for an undirected graph as the adjacency matrix would be. And then I'm also going to sometimes talk about the empirical graphon of a graph on n nodes. So if I have a finite graph, I can just look at the adjacency matrix of that graph, and I can say that any place that I have a 1, that I have an edge, I have a 1, 0, I don't have an edge. And I can just look at that as that finite graph as a piecewise constant graphon, okay? Okay, so now what is an appropriate metric for this? Now it's kind of obvious. It took us a year or so in the beginning. So if you look at what's called the Fries-Kahnen norm of a function, so now for the moment just think of W1 minus W2 as a function, this is breaking it up into all subsets such that you get the max cut. Okay, so just the sum of all the edges that you're breaking. Okay, now look at, so that's the cut norm. So now look at the cut distance between two graphs, W1 and W2. Okay, so it's taking the difference of them and seeing how do I cut it with the appropriate absolute values there. Now, we know that we don't want to have different things depending on how we permute the vertices, okay? So what I want to do is essentially minimize overall permutations, but here what that means is that I'm taking the inf over all measure preserving bijections, okay? And technically, I have to do a little more than that. These need to be atomless Borel spaces. And in general, I need to define it via extensions or couplings, or I'll make some errors in the general case. Okay, and a sequence of graphs is said to converge to a graphon in metric if the empirical graphons, that is the graphon which is just piecewise constant, which represents the graph, converges in this metric, okay, in this cut metric, which is Fries-Kahnen difference, but infed over all possible permutations or measure-preserving bijections. Okay, so in a series of papers with Lotzi Sr., Vera Shoge, and Kari Vestergambi, Christian and I first showed that a sequence of graphs is Cauchy in this metric if and only if it's left convergent and if and only if it's right convergent. So these notions that seem initially very, very different, limit of free energies, and like subgraph frequency seems local, free energy seems global, and the cut metric, well, everyone likes a metric because it just gives you analytic control. Okay, and then Balazs, Szigeti, and Lotzi showed that if you had a left convergent sequence, then you could use martingale convergence such that these limiting subgraph frequencies can be expressed in this way from the limiting graphon. Actually, Aldous had an earlier version of something like this, but it wasn't realized until later. Okay, and then we not only showed in this long series of papers that for dense graphs, left, right, and metric convergence were the same, but also that they were related to all these other notions of convergence. So this first one is the right convergence, but then convergence of any combination of max cuts and min bisections, or a convergence of quotients which are related to semi-ready partissues, or with David Gomarnik, convergence of a large deviation rate corresponding to entropies in the microcanonical ensemble when not only the vertex weights are fixed, but also the edge densities are fixed. Okay, and so for dense graph sequences, all these things are the same, which is really nice. It really makes you believe you've gotten a meaningful notion when these apparently different things are the same. Now, sparse graphs of bounded degree, we heard this morning a little bit about Benjamini-Schramm convergence. So that's a local notion which says choose a random vertex and look at the convergence of a graph rooted at that random vertex. Sparse graphs of bounded degree are very fragile. And what it turns out is that subgraph convergence, which is this very local notion, on a sparse graph of bounded degree is the same as this Benjamini-Schramm convergence of graphs rooted there. It is strictly weaker, so convergence of free energies is strictly stronger in the low temperature phase. High temperature phase, it's the same. And this large deviations convergence, which we had come up with David Gomarnik, is strictly stronger in any phase. Okay, so these things that were equivalent for dense graphs are definitely not equivalent for sparse graphs of bounded degree. But what we really care about are sparse graphs of unbounded degree. Okay, preferential attachment graphs, a lot of graphs, that model the networks that we are trying to look at are actually sparse graphs of unbounded degree, like a preferential attachment graph. Now, the cut metric is bounded by the L1 metric, which is the norm, okay, the L1 norm, and that goes to 0 if the graph is sparse. I mean, that is the density of the graph, so it goes to 0 if the sequence is a sparse sequence. So you kind of get a trivial answer out of this, and that's not what we want. I mean, it all works, but it's trivial. So we need something else. So what we said is, let us take our graphon and let us just divide out this density, okay? So what is that doing? That's taking this thing on the unit square, and it's blowing up everything as the W's are going to 0, as the norm is going to 0. And we'll call GN convergent if there is a graphon such that the cut distance of this to that goes to 0. So this is normalizing the density out. We call it rescaled, okay? It's just dividing out the density. And this turns out to be, this is the work that we did with Yufei. Finally, we did it, in 2014, and it's finally in press and transactions of the AMS. So this is equivalent to right convergence under suitable, or maybe this was number 2, which was published earlier, I don't know, under suitable regularity conditions. Okay. Now for sparse sequences, we see we see that problem, okay? There is another way, and this is what we did with Nina Holden, who was a grad student here, and our intern. Yufei was our intern too. He was a grad student. Now he's like a senior professor almost. Okay, he's been here for a while. Okay, so instead of doing this, why don't I, instead of looking at the unit square, why don't I look at the whole upper right quadrant? Stretch things out. So that means that what I'm doing is I'm multiplying by the square root of this L1 norm. So remember, this is going to 0, stretching it out, right? Okay. And I say that something is convergent in this sense if the stretched ones go to 0. And this is equivalent to a modified version of left convergence, which Christian will talk about, under suitable regularity conditions. Okay. The problem is that without extra technical conditions, mass can disappear. So it can leak out to infinity in the rescaled case, or it can leak up, or it can leak out in the stretched case. And so we don't get and we also don't get subsequential convergence for an arbitrary sequence. So the solution is to develop a theory for sequences obeying notions of regularity, which rule out these really pathological sequences. So Christian and I and Henry Conan Yufei did this for that rescaled case, came up with a notion called uniform upper regularity. And for the stretch case with Henry Conan and Holden, we did this for the stretched Graphons. So can we get a sequence which converges in both senses? Okay. And what sparsity can we achieve? Because you might say, well, this is nice. And okay, well, it turns out that if both sequences converge, then G is dense. Okay? So these are really describing different sequences of graphs, except in the limiting case when they're dense. Okay? And if either of these converge, then Gn has divergent average degrees. So we are not talking about something like a grid. Okay? This is unbounded average degree. Okay, so the advantage of the first definition is we can get things like power law graphs, and it turns out to be equivalent to right convergence, or these multi-way cuts, under the assumption of uniform upper regularity. The second definition, we get these very long tails, degrees of all scales. It can be generalized to sparse graphs under the assumption of uniform tail regularity. And then we can also extend the notion in the second framework from Graphons to Graphexes, which were introduced by Veitch and Roy, and we get compactness and subsequential convergence without the assumption of uniform tail regularity, although you see a difference in the limiting object if there is or isn't uniform tail regularity. Okay, so non-parametric graph modeling. The traditional approach here is the stochastic block model. Okay, so that goes back to 83. So I assume most of you know what a stochastic block model is, but in case you don't, think of, k different species of particles, k colors, and I have a probability that a red is connected to a red, a blue to a blue, green. Probability that a blue is connected to a green, a blue is connected to a red, a blue is connected to a yellow, so on. So I have these k choose 2 parameters, which are the connection probabilities. And what I'm going to do is I could just go in there and I could just scale these with the density to obtain a sparse graph. This is what people were doing for years in actual estimates. They first determined the group layers via clustering or belief propagation or something, and then they averaged over the adjacency. They averaged the adjacency matrix over all edges whose endpoints had those colors. They were assuming it was a block model and figuring out what's the best block model. The problem is that it's unclear if there's any stability under misspecification. So if it's not a block model, what am I getting? Okay. So here's an alternative non-parametric approach. Turns out that it actually goes back to 2002. It was in the Lovash-Seghetti paper. Also, Bolobash, Janssen, and Reardon did some really nice work. And then we did some stuff on it in 2015. So if instead of a matrix indexed by communities, you use a function based on features, okay, so I have a feature space with a certain probability distribution, a graphon, and a target density. So what I'm going to do is I'm going to choose my features according to some probability distribution pi. So let's say I have people who are on Facebook, and for each person I have a height, a weight, an IQ, an income, various things. Okay, so that's my XI. Okay, state they live in, whatever, and then what I'm going to do is I'm going to have some function W, and I'm going to say, oh, the probability of someone with this set of features being connected to that set of features is given by flipping a W-weighted coin, and I'm going to scale by the appropriate density, okay, so that I don't get a probability bigger than 1. We call this graph an inhomogeneous random graph with target density rho generated from the graphon W, the random function W. W is a constant. We get the Erdős-Rényi random graph. It's more complicated. We get more complicated things. And what our theorem says, so this is with you, Faye, actually, is that if the rescaled W's converge that the rescaled W's converge in this metric, in the rescaled cut metric, if the density is going to 0 and the average degree is diverging. Okay, so this has strong relationship to this rescaled graphon that we were talking about. Here's a totally different way of doing things. So that other one was more of an analytic, probabilistic approach, okay? It's very nice to fit it to certain graphs. If you're concerned about every graph being a superset of the one before, it could be a problem because you're dividing out by a density, okay? So this is a very different way of doing things. Carone and Fox, that should be an F, not an R, Carone and Fox, 2014 came up with something, and then you should also see Veitch and Roy, who did a very nice, generalization of the Carone and Fox and went much further. So I have a sigma finite measure space, and I have a graphon, just a function, a symmetric function of two variables. And now I'm going to let something be the points of a Poisson process with intensity T mu. Mu is the measure on my space. And I am going to connect I and J. So remember, I could be, you're being born with this whole set of features that Facebook may know about you or something. And I'm going to connect with that probability. And then I'm going to remove isolated vertices, and I'm going to return to you the finite graph. So let's look at how this would work. Here, I'm just showing them in one dimension, but you can imagine this being in a much higher dimensional space, like, the 4 features I said to you or other things, okay? So they're born with these features. And then I go and I flip my W-weighted coin, and it turns out that X2 connects to X3 with its appropriate weighting. They turn out to get connected. X2 connects to X4. 3 and 4 don't connect, and 1 doesn't connect to anyone when I flip these coins. Okay. Then, a little while later, 3 more individuals have been born with their set of features. I check all the pairs, and I see that 6 has connected to 2 and 4, but nothing else. 7 has connected to 1, so now 1 appears. So 1 was kind of waiting there, born, but nobody had connected to them yet, okay? And 5 is now waiting for love, okay? And the relation of this to stretch convergence is that this process converges to W in the stretched metric, okay? So 1 is more of a probabilistic analytic way. This is more a little bit of a statistical way, okay? But they each converge in their appropriate metrics. Okay. And this is kind of how they look in some, they're more spread out in the second one. For the rest of this talk, we're going to work with the first model, and Christian will focus on the second model and on Graphexes. Okay, so estimation and machine learning. So the idea is that I want to estimate W by the best k-block approximation to the adjacency matrix. Okay? So I'm going to do a least squares algorithm. Okay? I do least squares so that I don't land up dividing through by 0, which happened with things that people did before. Okay, so I'm given an input graph with an adjacency matrix and an integer k, and I want to find the best block model, the best k-block model approximation to that adjacency matrix. Okay, so I want to minimize overall, so I take it, I test it against some block, some block model. I do all the permutations of the block model so that I'm at least lining things up properly. And then I find the minimizer of that, and that I call B hat, okay? And I'm going to output that, which is the empirical graphon that corresponds to it. So I'm going to get this B hat, which tells me, like, red is connected to blue is connected. That's the best match. Okay, and this is also a long argument. This was with Henry Cohn and Shishendu Ganguly. It's now at Berkeley. And so as n tends to infinity, this gives the best block model approximation to W in like an L2 version of the metric, as long as W is in L2, so which is not that difficult a condition to satisfy. The density is going to 0, and the average degree is blowing up. Okay, and so this is an estimation theorem. When I went to my first NeurIPS at some point, I don't know, probably 7 years ago, or I don't know when it was. I hadn't gone to a NeurIPS before then, and these people came up to me and they were like, "Oh, we're using your Graphons to do estimates on real graphs." And I'm like, "What? Really?" I mean, they said, non-parametric stochastic block models, which I had also never heard of, so maybe longer ago than 7 years, I don't know. But I didn't know what they were talking about. But I saw all these people using it and fitting it, and I'm like, "Oh, do you have, like, statistical consistency theorems?" They just looked at me like, "Oh, why would we need a statistical consistency theorem? We just do it." So, but anyway, so we went and proved a statistical consistency theorem. Okay, so private networks. Okay, even for databases, not networks, we know it's really hard to make them truly private, right? And it's actually a lot worse with networks. Because via your connections, I learned something about you. So already in like 2009, some people inferred with high accuracy sexual orientation of people from their Facebook links, okay? There was nothing on that person's site which would, or they weren't looking at any content on that person's site, okay? They were just looking at the people to whom they were connected, where they had some ground truth about sexual orientation, and they can infer, or where there were a lot of likes going back and forth or something. And so it's really hard to get privacy on a network, right? Your connections reveal so much about you, and you don't want just a naive anonymization. Okay, so a lot of people have heard of differential privacy in the database sense. Okay, there is a notion of differential privacy. There are a couple of notions for a network. The stronger notion, and the one that we look at, is called node differential privacy. And what that tells you is that if I pull any individual out of the network, just a single one, the probability, so if I have a randomized algorithm, I say that it's node differentially private, the probability of any event with or without that individual pulled out, say it's epsilon node differentially private if it's about the same, up to, for small epsilon, like, 1 plus or minus epsilon, whatever. And so this is a good notion because this means, in particular, if you pull me out, you get the same answer for any question you would ask with this algorithm, okay? So I'm happy with that. There's also an analogous definition for edge privacy. This is much easier to achieve but less useful because that's talking about not pulling out an individual but pulling out a connection. Much easier to see what that would do, but it's also not what's really relevant. You really can, you're a node, so you care about the nodes, okay? And so previous work was edge privacy or dense graphs. So the idea is to use the exponential mechanism. So I want to output a sample from these block models that are close to it, and I want some little bit of noise in there, lambda. And this is something that was used in differential privacy. I mean, it was Kunal, Talwar, and Frank McSherry, I think, who had come up with this mechanism in the case of, or this is the analog of what they did for the graph case. And so working with Adam Smith, who is one of the original differential privacy people, and also with Adam and Ilyas last summer, Ilyas Sadek, who's here, I think, someplace. I mean, I don't know if he's here, but he's at MIT. Okay, so now we can't do it for W in L2, but for W in L infinity, and density going to 0 and average density diverging like log n over n, it is possible to get it to be node differentially private. That is what we first proved with Adam in the Nurips paper in 2015. And then with Ilyas and Fox last year, we proved that we can get upper bounds which match the mini-max lower bounds in the case of no privacy. So you're basically not even losing anything doing this, okay, on the upper bounds, which we were really happy about. Christian had been trying to prove that since 2015, and poor Ilyas, we threw it at him. Oops. Like, don't throw that at him. You've been trying that for 2.5 years. It's not a nice thing to do to someone in a summer internship. But anyway, Ilyas did very well. Okay. So we saw we have graphs represented by vertices and an adjacency matrix telling us whether they're connected or not. We can take limits of them, and we get graphons, which sit on a sigma finite measure space and are characterized by a symmetric measurable function. They can either be ones. So then we can get nonparametric random graph models either by just taking this W, scaling it by the density of the graph we'd like to have, drawing these vertices randomly and connecting them with probability, which is 1 over the density times the W for those two sets of features, the sets of features that describe the two nodes. It's one way of doing it. The second way is that I have a Poisson process of points, okay? And I look at what has been generated at some time. I flip again according to this W, and I connect things where W, where what I draw according to W tells me that they should be connected. I have this reserve, people that Zuck is trying to go after who've been born but are not yet on Facebook, okay? And I keep doing this, and here I don't have to scale because what happens is it's getting thinner and thinner as it goes further out, Okay, so those are those two different, yeah.
The second model that you described with Poisson process with increasing density, effectively that gives a sparse graph generation model, but still with the dense graphons.
No,
Over a sigma finite space instead of a probability space.
But your sort of W could be sort of still in a, at least sort of traditionally you have a graphon with sort of the entries for every xy, which are sort of non-trivial, so it's not
If it's just ordered on a compact set,
then it's dense. Then it's dense, and then either method can get that for you. And if it's not dense, okay, if W is living on the whole upper right quadrant, okay, then, okay. So, right, because my X's are now, yeah.
Are you done with the privacy part?
Yes, I'm done with the privacy
I
part.
have a question on that, and that is, it seems to me that by using a Graphon formalism, you're making it very easy to be private, in a sense. Because basically what happens in a Graphon is that everything that happens will happen infinitely often. Right? So if you, any structure that you have infinitely often. And so it seems to me if you pull out a single instance, it's very, it is not so surprising that it would vanish in the limit. So I feel if you like have something more like for your point tree limit or something like that, anything you can identify in the limit can probably not be private. Right?
I guess that's,
an interesting question, yes. I mean,
we had
even
never
here
thought of it
it's
in that
not-
way.
It turns out not to be that trivial. So if I give you,
No, it definitely wasn't. Ask Ilias.
so if I give you a random graph, okay, an Erdős random graph, and now I ask you to be sort of differential private in the worst case, you're just supposed to estimate p. It turns out that's the problem I gave to Ilias. Turns out that it wasn't the upper and lower bounds what you can do differentially private were different by a square root. So it turns out that even that problem, which seems super trivial, right, just estimates the density, but privately. If you were edged privately, it would be super easy because you have the sums of independent random variables and you sort of.
What I mean by easy is not that it's easy to prove.
No, no, no.
Easy
You're
for
saying
something
it's
to be
easy
private,
for something
right?
to be private.
Yeah.
Because because my inference gets sort of averaged out.
Yeah, exactly.
Yes, okay, okay, yes.
So you're removing that one pattern,
Yes,
but an equivalent pattern will occur over.
yes,
Like in your
Yes,
for your point
yes.
tree models, that's very different.
yes, yes. So, yeah, probably, I mean, it would be nice to look at those models and prove that you can't do it privately, which I think would be the result, right?
At least for like a large.
Yeah. I mean, of course, you can come up with examples where it's private, but
Even that problem you have here, right? In WSNet, you have large equal vertices. And so you have to do something.
although we did it for W and L infinity.
That is true. But even there you could have, so you could, since I'm
It's not absolutely bounded, it's in L infinity.
differential privacy is the worst case. So maybe the average degree is 1 over square root of n, or maybe it's very low, I think it's log n over n. But there could be a vertex which has much higher degree. And so you have to deal with that in order to, because otherwise, right, you want to, it's just like this.
Okay, I've got 5 minutes. What I'm going to do is I'm going to just mention there are 2 applications we're thinking about. The second one was the one I was going to talk about, which Christina already talked, they're both with Christina, talked about. This is, a recommendation or a network completion algorithm or a weighted network completion algorithm, who should be connected to who. If I'm doing development economics and I've done some very sparse sampling, how do I know what other connections there might be? Okay, so it's a matrix completion problem. If we use just good old Aldous Hoover, not sparse Aldous Hoover, if we use good old Aldous Hoover, this says that these, because we have exchangeability and ergodicity, that these guys are just functions of the features of the movies, the features of the people, which we don't know, they're latent, and some IID noise, Okay, and now if I take the expectation over that, I'm observing each entry independently with probability p. So this is how I'm sampling the Netflix graph, the potential Netflix graph. This is the dimension of the latent space. I could take the larger one if I wanted. Can we learn, given the observed one, can we learn its expectation or maybe even its distribution? And ideally, what you really want to do is you really want to estimate this for something like p goes like 1 over n, okay? Because I don't want to have seen, you know, a positive fraction of the stuff there, right? And so Chatterjee had some nice results, but still it wasn't useful for really large n if you actually wanted to do that. So now I've got Christina's slides, which you guys saw. I do an expanding neighborhood until I find some overlap. As she very nicely explained to you, this is, well, okay, so here, this is as far. This is a simpler case. This is as far as we have to go, where p is the sampling density. We're going to compare ratings along those paths. So she was showing you in the much more difficult case of the tensor. And the result was a very nice result relative to previous results. And then she did more beautiful stuff with it. And it may even be simpler now, right? Better now, I think. Okay. Okay, so summary. For dense graphs, we have metric convergence. We have left convergence, which is subgraphs. We have right convergence, which is free energies for all these models characterized by these little coloring graphs, and many other global notions of convergence. For sparse, unbounded degree graphs, we came up with this way of rescaling, which in order to get convergence, we needed uniformly upper regular, which I'm not going to define for you, but it's a pretty natural notion. I mean, once you get all the definitions, it's pretty natural. Or for the ones where we stretch, uniformly tail regular. And Christian will talk a lot more about the second notion. We can use these to generate random graphs. So if I give you a W, you can either, if I also give you a density, you can generate them in this first rescaled way, or you can do a Graphon process, okay? We can consistently estimate very general W and L2, like power law graphs, okay? We can consistently and differentially privately estimate for W and L infinity. And Christina can give you improved matrix completion algorithms. Okay, now it's time for Christian.